So I think most of you know me from, I started my postdoc in October, and I'm going to give a short review of my research so far. So I'm going to use my defense slides today. It's a bit longer, I think, than 20 minutes, but I'll start with the talk and then maybe skip some more theoretical parts as they are a bit complex. Okay, so to the Okay, so to give a brief introduction of myself, maybe, I think most of you don't know my background because most of the stuff you will see today is not about robotics or core robotics like control methods, but it's more about statistical approaches to evaluate safety of robot systems. Because my background is actually physics, so I started my studies in Karlsruhe, which is a city in Germany. It has a technical university there. And basically, I focused on particle physics in the experiment called Karlsruhe tritium neutrino experiment. And the goal of this experiment is to measure the neutrino mass. The neutrino is a particle which has a mass, but it's the lightest massive particle we know about today. So it's really challenging to measure this mass because it's really tiny. And during my bachelor's, I focused on the particle decay. So what you can see here is the decay of the tritium atom, which is the isotope of hydrogen. And the red particle shown here is the neutrino, which is the most interesting particle in our experiment. And during my master's, I focused on the particle collisions at the end of the experiment in the spectrometer part, which is a bit challenging because the spectrometer is the biggest part in the entire experiment. And since this experiment was really big, we had a lot of collaborators also, which gave me the opportunity to do my master's thesis or part of it in the US at CMU. And there I basically focused on developing an ion collision energy spectrum software. So in this software, the goal is to derive the collision spectrum for these ions who collide in the spectrometer section. And also during this project, I transferred this software into another experiment called TRIMS, which is located in the US. And then actually I started my PhD in physics in 2017. And then I decided that I want to do something more in the direction of applications, which made me apply to the domain of robotics in December, or it was, I think, October. And then I started in December 2018. And first I started working with Thorsten Krüger, who was my first supervisor until 2019. Then he had left to Google. So I had to switch into the direction of humanoid robots or mobile platforms and bimanual manipulation with Tami Masfo. And so during my PhD, I basically transferred some statistical methods from the domain of physics to robotics. And here safety was one domain where, this worked quite well, as we will see. So to start with the research part, I'd like to first outline what I mean by safety, because there are different labs in Germany as well, like the lab of Sami Haddadin as well, does some research on safety, and other labs, like I think also Wolfram Burgert and KIT basically defines safety by the standards which are provided by the International Organization for Standardization. So maybe you have seen this sign here, which stands for this organization, and basically these standards are used to certify technical devices in general. So I mean smartphones also and sensors in order to make them like available for the community, they have to be certified by these ISO standards. For example, this also goes for cars, like for road vehicles, you have ISO 26262, which tells us how the fault and the failure can be defined. Also, there are quantitative requirements, but we are going to focus on the human-robot collaboration setups, where we have 3 most important ISO standards given by these. And depending on the robot and the robot mode, which means it depends on whether we have a force torque sensors or not, we have some distance and velocity limits for this collaboration mode. And we also have limits for the accepted failure rate, which amounts to 1 accident in 114 years. So this is a really strict limit when it comes to human-robot collaboration without force torque sensors on the end effector. Then we have the definition of the risk, which is given by the product between the severity and the probability for the occurrence of an incident I. And if we now can satisfy all these limits, we can say that our system is safe. However, this is not the case because normally we cannot accurately measure all these values. So if we want to measure the human-robot distance, we can obtain the position of the robot end effector in most cases, but we don't know much about the human hand position. And there are some uncertainties, which is the reason we cannot be accurate and not be sure that we meet all these limits. So in the end, this measurement uncertainty UD is one origin for the occurrence of risks. And if we know this measurement uncertainty, then we can derive some countermeasures to develop some safe and trustworthy robot systems. Okay, so if we look into literature now, there are different uncertainty determination techniques and also different uncertainty understandings. On the one hand, in robotics, we have methods using probability theory. Those are the most traditional methods. They suggest the development of belief space planning algorithms and filtering methods. Most of them are, I think, developed by Wolfram Bogart, who is now in Nuremberg. Then recently, methods have been suggested that use neural networks, where the goal is to learn the uncertainty in the training data. And here they distinguish between the data and model uncertainty. So the uncertainties which is inherent to the training data, and then the model of the neural network. Then in natural sciences, so the first part I mentioned, in, which I used in physics, uses the metrological notation. And the difference here is that metrology uses SI units all the time, which means meters for distances and seconds for the time. And yeah, those are really established as well. And especially one can understand them and trace back. So this is not the case, for example, for neural networks. And if we want to compare these three methods now regarding the suitability for robot systems, the goal would be to somehow find a representation that can combine all of these together to one uncertainty measure. And this was the first contribution of my thesis. So I derived one unified uncertainty representations via the reinterpretation of parameters, which was basically theoretical work. And then in the second part, I was able to show that this derived uncertainty representation can help to optimize the performance in robot applications, where on the one hand, I focused on the risk reduction and then also transferred that to the improvement of the grasp success rate in bimanual manipulation. The central research question was given by this one. So how can the uncertainty quantification and propagation methods be adapted to improve the performance in robotic applications? So there's also a theoretical formulation of that. So you have an optimization, which means in that case, a minimization of the maximization of a property. So this is given by this pi here, and the minimization of risks can be formulated like that, as well as the maximization of the grasp success. If you have given then the robot systems, you can describe this by state variables or other parameters and define the critical parameters in which you want to perform this optimization goal. For example, the time, or it can be also spatial ones. Then you, I will show how we then can calculate the uncertainties in these applications and the sensitivities, where the sensitivity captures now how the input change of a system affects the output, which is basically the optimization itself. And in the end, we will measure our optimization performance by calculating the distance between the actually achieved value and the optimization goal. Okay, so this is the list of my publications, but now I'm going to focus only on 3 of them because it's, the rest of it was not too important for the contributions here. The basic pipeline is shown here. So in the first step, we have to specify the optimization goal, which can be the risk minimization or the maximization of some success rates, and basically the function pi. then for this function, we quantify the uncertainties of each of the components. So U is the uncertainty and X1 is component 1, X2 is component 2, and PC denotes the parameter space. Then in the next step, we will show how the uncertainty can be propagated along the pipeline to derive the total uncertainty of the application. And this can be then used to optimize the robot systems. So the first 3 steps are basically theoretical work, so I'll try to be a bit fast about them. In the first case, we have, in the best case, the manufacturer specifications of the device we are using, like the camera or a laser scanner, but we might have also some black box components where we don't have any information on the uncertainty. So in that case, the first idea, or my first publication, was about deriving some conservation equations based on invariance of the system. So we formulate a system invariant with respect to a critical parameter space P, and then so we record some data with the black box component and evaluate these conservation equations. Then we derive the violations on that and can deduce on the uncertainty. So for example, if we have the black box tool for object detection, we might take some data on static objects where we do know that they will not change their position over time. So in that case, PC, the critical parameter would be the time. And the conservation equation would look like the equation on the first line, telling us that the object position does not change over time. And if we now can measure some violations on the 0, so like that we have larger values here, then we can deduce on the uncertainty of the device. Same goes for human joint detection in 3D space. So if we track one human, this human does not change its size over time, which means the length of the body segment should stay constant. If that's not the case, it's due to disturbances we do not want. And this could be validated on the safety scanner 6. So in this case, we had some manufacturer specification provided by SIG. We assumed that it's not given and applied our method and found that the results are close to the manufacturer specifications, and that the discrepancy comes due to the limited amount of the data we recorded here. So now we know that the black box component uncertainty can be estimated by this method, and in the next step, we will have to propagate the uncertainty along the pipeline. And as I mentioned in the beginning, we have here the problem that we have different representations. So the metrological representation of sensor devices or other technical tools we use, and the understanding of uncertainties in the domain of learning. So we have another definition of uncertainties for neural networks and also for classifiers. So basically what I mean by classifiers is something like this. I think most of you know this MNIST data set or digit data set. If we have something like this 9 and then we provide it to the network, we would expect in the ideal case a result like this on the right-hand side. So we have a vector that gives us the digits from 0 to 9. And in the best case, we would have a classification of 100% for the 9. So in most cases, this does not happen. We have something like 98%, maybe 99 point something. And this discrepancy comes from the uncertainty either from the model or from the data set. Distinguishing the uncertainties in model uncertainty and data uncertainty is not does not help us in propagating the uncertainties, although. So this means we have some discrepancy between these understandings, between the metrology and the neural networks or the learning domain. But there's another measure in the learning domain, which is called the robustness. And this actually measures how an input distortion affects the output. So this robustness basically tells us what happens if we vary the input data point x0 by a delta x, and also measures whether we can get the same output y for this varied data point x0. To be a bit more specific, this is how it is done in theory. So the robustness is defined by an LP ball with a radius delta. And here we are discussing this example on the data point x0. And if we now consider a larger radius, so, and we let this ball grow, we can see that the data points x1s and x2 are also covered by this ball. And now the question is, if we still get the same result for this y when we have a larger ball here. If that's the case, we can say it's robust against these variations, and if not, it's not. And then in addition, the learning domain distinguishes between the local robustness and the global robustness, where the local robustness now says it's okay when it's only, when this condition is only held for the x0, and the global robustness now tells us the robustness has to be satisfied by all input data points. However, this requirement might be too strict for robot applications, as the first one is maybe too weak because we want this to be satisfied for a certain set of input data points. The second one, however, might be too strict because it takes a lot of computation times as well, and we might tolerate some disturbances in some regions. So my idea first was to map this distortion of delta on the technical devices, because this is a theoretical measure only for neural networks. And I thought maybe we can map this on some camera devices or technical tools to make the combination with the metrological sensor uncertainties easier. Then, since the local and global robustness may be too strict, my second idea was to introduce a probabilistic setting, which means we don't consider all the input data points, but only a fraction of them. So we calculate that for each of these, and then introduce this Lipschitz equation telling us, okay, we have to meet this requirement with a certain probability p, and then exclude also some regions for meeting this requirement and reduce the computation time of it. And with this probabilistic robustness definition, I suggested a reinterpretation of the parameters. So lambda is basically the limit provided by the ISO standards, then the sensitivity K, and the confidence value, which is shown in blue. And in my case, the confidence is actually something different from the uncertainty, because the uncertainty tells us about the actual deviation, while the confidence gives us some information of how much we can trust this uncertainty measure. So actually, I think this addresses the problem of this question well, because in that case, we had to first fix the reference data x0. So we have to fix what's the ground truth now. And we assume that this is now noise free. So if we have some reference data x0, which we captured with the camera, for example, a RealSense camera device, where we do know the uncertainty of, and we can disturb this. So what you can see here below is some disturbed input x0, where we changed the lightning conditions as well, but we used the same device for capturing it, which was the RealSense D435 camera. And by now comparing these two, we can find some calibration measures for the sensitivity and the confidence, which I reinterpreted. And to find out how much we can vary the delta to get the same result, which means the result for this 9, because it's a 9 which we use as input here. We can find out which parameters fits best for our experiment. So this is what was then done actually in the next step. So this is, maybe it's a bit difficult to understand, but I will try to explain it. So we did some calibration of the parameters with the digit classification MNIST and another data set which is called GTRSB, I think, and it contains some traffic signs. What you can see on the y-axis is the rate of wrong classifications. So if we have a really small delta, so a really, really small ball around this x0, we have only like wrong classifications because the ball is too small. And if we make it a bit larger, we have a plateau here. And if we make it even bigger, then we can at some point capture the uncertainty of the technical devices we use, which is this camera in that case, but it also contains some environmental disturbances. And by showing this, we know now that if with this reinterpreted version, which is shown on the upper side of the slide, this probabilistic formulation of the robustness, we can combine the camera uncertainty and the ones of the neural network classifiers. And this eta here in the last line shows us that the performance could be improved because we want the eta to reach 0, which is the best case. It was 60 before, and then we could reduce it to 39.8. Okay, so I think this was like a lot of theory, and yeah, so with that, with the 2 steps, quantification and propagation, I was able to publish 1 paper, and the next 2 are now the robot applications. So first, the optimization is formulated with regard to the risk reduction in human-robot collaboration. And here we use these ISO standards I presented in the beginning. So what you can see here is that we use the for human joint detection, the framework OpenPose 3D. You might have heard of that. So we have the anti-factor position of the robot, and this robot has to stop once we exceed a certain distance. And now this OpenPose 3D is treated as a black box because we don't know much about the uncertainty. Of course, OpenPose delivers us some uncertainty measures, but we cannot understand how it calculates it. So we cannot be sure that it's actually the truth. The critical parameter is given by PC, and we use the conservation equation I mentioned before because the human joints or the human does not change its size. And we then map it to the critical variables and the limits given by these ISO standards to evaluate safety online. So in that case, the uncertainty in the joint detection is directly mapped on the safety standards to estimate whether we exceed this 1 accident in 114 years and whether we meet this distance values given by these standards. So ISO 13849 tells us 1 accident is tolerated in 10 to the 6 hours. We have the camera frame rate, and then we can map this frame rate on these 114 years, apply statistical methods to estimate the sigma range and the mean value, and then find out how large the uncertainty is for each of the body segments. And by weighting these body segments, we can then estimate or evaluate these safety standards in ISO 13849. And this is done online. So this is the picture for 1 frame rate and for 1 frame. And if we apply this method, you will have something like a warning once you exceed the given limit. Okay. In the next step, we transferred this method to the grasping application. So here now the optimization is not the risk reduction, but the maximization of the grasp success. And in that case, we assume that the uncertainty models are provided by the action extraction fusion. So what you can see on the right-hand side is the AMA. It's a mobile platform, and at KIT, we focus on bimanual manipulation mostly. And AMA is now supposed to grasp some objects out of this box in a successful way in the ideal case. And for that, it generates some grasp candidates, as we will see. So these green boxes here are the grasp candidates, and normally it generates around 100 to 110 grasp candidates, and out of them, we hope that it will grasp the most successful one, or the one with the likelihood for the highest success rate. We assume that these grasps are generated before, and the uncertainties are calculated by a Kalman filter and the hidden Markov model. And now we want to optimize the grasp selection regarding the success rate. So here we say that the optimization goal is given by the rate, and the critical variables are given by the height of the grasp candidates, the distance to the object center, the manipulability of AMA, and the support graph. And the support graph basically tells us how many objects lie below the object of interest. Then we collect some data and generate some probability density functions. And this training data is then used to derive an optimization function in an understandable manner. And with this optimization function, we perform a second round of experiments to see whether it has helped or not. So each grasp is actually modeled by uncertainty distributions, and we use some Gaussian models. This means that each of the metrics I presented, which is given by the height, by the distance, the manipulability, and the support graph, we obtain some probability density functions. Because those Gaussian distributions on the left-hand side add up, and we collect 1,100 grasps in real world, and then we obtain the ones on the right-hand side. And of course, each of these distributions can now be divided into a success or into successful grasps and failed grasps. And based on these, we derive an uncertainty and sensitivity optimization function, which is given by the global sensitivity represented by the Kullback-Leibler divergence. This basically measures the distance between these two curves, and a local fraction that is based on the likelihood values here. And then we add up this values for all of the four metrics and call this score Z, and calculate that for each grasp candidates. And in the end, AMA grasps the one with the highest Z here. What we could see is that we could increase the success rate from 32.6 to 73.8, which is a large increase. We also tried this actually with only considering the height of the grasp, because we thought that it's the most influential measure. However, then in that case, we only measured something like 50%. So it means like these 23% to 73.8% somehow comes from statistical correlations between the matrix, or the distance to the object, which was also an important thing. Okay, so we can conclude from that the consideration of this probabilistic models yielded an improvement, because before we didn't model them with Gaussians in the random selection mode. And because we have some correlations between the metrics, it might make sense to collect a higher amount of data, but actually collecting this 1,100 real-world grasps took us almost 1 week. So 1 week we had to collect them every day for 7 hours or something. So in the end, it will be a bit challenging to collect more data on that, like 10,000 or something, which will deliver us with a higher statistical significance. Okay, so the major contributions of my PhD were that. So the uncertainty propagation in one representation by unifying these measures with this Lipschitz equation. Then, combining this with the sensitivity-based optimization to improve the performance and safety and grasping. And the future work would be to minimize the risk in human-robot collaboration. So that was at the point of July. Of course, I didn't know what I will focus on here. And so I couldn't put that at that point. And maybe there will be some neural network-based applications beyond the classification. So I'm not sure how it will influence imitation learning. I think this might be an interesting aspect to study as well. And this is an overview of the recent and current projects. So I started one with University of Stuttgart. There the goal is to reduce the failures for industrial robot manipulation tasks. So we started with pick and place and object shifts, which worked quite well. But so we will have to extend that, and the plan is to submit that to Dyros basically. Then there's a collaboration with DLR, the German Aerospace Center. And here the goal is to explain the uncertainty sources via sensitivity in robot perception. And right now we're working on point cloud registration and estimating the sensitivities in that. And we will probably validate that in March and April on the Toro application. So we will start with a really simple application where the Toro has to perform similar tasks to the AMA and extend then the use case to human-robot collaboration maybe. Then, of course, there's the Alchemist project. So I was thinking of failure reduction here as well. So imitation learning is also something where we could apply these uncertainty determination techniques. And actually last week I talked to some KIT students who are a bit more experienced, I would say, in imitation learning. And they said that that it might make sense to add some interpretable modules to imitation learning framework, ACT or whatever, because these frameworks are really sensitive to changes. So to track some failures and to reduce them, it helped a lot to add them. So they focus on visual imitation learning, and they use some geometrical methods, I think. And in their paper, which I read, it shows that it actually makes it more robust against changes, and that we can track how changes improve the performance of these applications. Okay, so this was an overview, and thank you for your attention.